Welcome to the 12th video in Special Relativity and the second last video in topic 2. In this video we will be looking at relativistic energy, and we're going to do that the same way we started by looking at momentum. So we'll start with the two things about energy that we know must be true. So we know that by M inertia, we know that in an isolated system energy must be conserved, and we know that at low speeds our energy should approach our classical value. So we'll start by looking at the kinetic energy. So we know that the kinetic energy is equal to the change in work, which is equal to the total amount of force required to increase that object's speed from 0 to its final speed, here called u. And we know that our force is equal to the rate of change of momentum. So if we substitute that value into our kinetic energy equation and simplify, we find that our kinetic energy is equal to the integral of the velocity of our object with respect to the momentum dp. And we saw in our previous video that our relativistic momentum is equal to gamma mu, where u is the relative velocity of our object, and substituting that in, we get this equation here. So we get an equation for the integral of u with respect to du. Substituting in our expansion for gamma, that gives us that our kinetic energy is equal to the mass times the integral of 1 minus u squared on c squared to the power of 3 on 2, integrated over du. And the result of that integral, which I will leave up to you should you wish to do it, is this equation here. Simplifying that, or using our expression for gamma, we find that our kinetic energy at relativistic speed, so our relativistic kinetic energy is equal to mc squared times our factor gamma minus 1, where our factor gamma depends on the relative velocity of our object. So now we have to check. So we need to look that this equation also satisfies point 2, that at low speeds this kinetic energy should approach our classical value. So as our fraction u on c approaches 0, so for very small relative velocity, we can use the binomial expansion for gamma. And beyond our fraction u squared on c squared, that term becomes negligible. So that gives us that as u on c is approaching 0, gamma is equal to 1 plus half u squared on c squared. And substituting that back into our relativistic kinetic energy equation, we find that at low speeds we get a kinetic energy of half mu squared, which is our classical value. So we now have an equation for our relativistic kinetic energy, and if we expand that out, we can see that it has two terms. It has a term that's dependent on the relative velocity of the object, and it has a term that is independent of that velocity. And we also call this independent term the rest energy, E0. So this rest energy is something like the potential energy of an object, and every object that has mass has this potential energy. So we know then the total energy of an object is equal to its inherent energy, its kind of potential energy, plus any kinetic energy that it has. So substituting in our equations, we then find that the total energy of our object is equal to gamma times mc squared. So this energy, gamma times mc squared, is the energy that must be conserved in an isolated system, and not its more famous counterpart, E equals mc squared. So we get to the famous equation E equals mc squared as we've defined it as our rest energy. So when the kinetic energy is 0, then the inherent energy of an object with mass is equal to mc squared.